Hello, this is video series for lecture of Chemical Engineering Thermodynamics I, and this is the part 1 of lecture 2A. In the last lecture, lecture 1B, we discussed the application of the first law of thermodynamics to isolated system and to closed system. Especially for closed system, the first law would be stated that the given energy in terms of either heat or work would be applied to the change of internal energy within the system. For this lecture, we will discuss a little bit in more detail for the first law in closed system. Okay? So this is from lecture 1B, and if we apply energy either in terms of heat or work into a closed system with internal energy U1, the system would change its state into the final state that has the internal energy of U2. Okay? If we neglect kinetic and potential energy of the system and the assumption that our system does not move, so the kinetic energy change or potential energy change remains 0, and we can drop these two terms from the first law, and we will end up with delta U total of the whole system would equal to the energy transfer as heat or work into the system. Okay, may I remind you that the left hand side of the first law states the change of internal energy within the system, where the two terms on the right hand side indicate the amount of energy passing through the system boundaries. Okay? Further analysis of this closed system can be divided into two extremes. The first extreme is the closed system in which the total volume of the system remains constant or unchanged throughout the process of given energy. Example of this closed system with constant volume is shown in this picture. This is just a scientific experiment. You bring some solution into a beaker and put it on top of this magnetic stir. Okay? If we define that the liquid itself is a system, I can draw the red dotted line here around the liquid and define it as our own system. Okay? And since if the liquid does not evaporate, it remains in liquid form, we can say that the liquid itself does not change its volume. Okay? The volume here remains constant, and there is no evaporation moving out of this dotted system. Therefore, we say that this is the closed system. Okay? Anything outside this dotted line is called surrounding. You can say that the air around this beaker is considered surrounding. You can also say that the heater itself is surrounding. Alright? If we said that the effects of the heater is more significant than air at the moment, because the temperature of this plate, this hot plate, is much higher than temperature of the liquid, so there will be the temperature difference to induce heat transfer from outside to inside. Okay, and if we say that the heater is more important in this case, we will say that heat will be transferred from surrounding, which is our heater, into the system, which is our liquid. Okay, of course, at the same time, you may say that temperature of the air may be a little bit lower than temperature of the liquid. In that case, there must be heat transfer to the air as well, and air will be considered another set of surrounding. But for this simple problem, let us assume that the temperature of the air is not so much different than temperature of the liquid. So the surrounding that we consider at the moment would be just the heater. Okay? Another thing that we have to consider is this swirling of this liquid. The movement of the liquid is caused by applied force. Basically, liquid itself does not move. We have to stir it. Stirring means we apply work into the system, and this work is mechanical work. Okay. If we recall from last lecture that there are two kinds of mechanical work. The first one is called expansion work. The second one is called non-expansion work. If we look at this picture, as I stated earlier, the volume of the liquid does not change, so there is no expansion work in this case. The stirring action here is called non-expansion work. Okay, so we give the system work, so there's a W here going into the system. Okay, so in this case, both W and Q would have the sign to be positive because we supply the system with energy. If we scaled it up in engineering application, okay, the system that looks similar to a stirring beaker would be this equipment, which is called reactor. If you have the, basically it is called stir tank. But if you use this stir tank as a vessel to conduct reaction, inside there will be reaction, then the equipment would be called stir tank reactor. Okay, if you put liquid in there or reactant in there, you stir them, then the reaction takes place inside, and you wait until the reaction completes and drain the products out. The operation will be done in batch, and this is what we call batch reactor. If you recall in lecture 1A, we can control the temperature of this reactor by supplying steam in this gap here, which is called jacket. Okay, if the steam is supplied to jacket, there might be the inlet for steam and outlet for steam coming out. The supply of steam is basically the means to apply heat to this reactor. Okay, the reactor itself, the system is still defined as the liquid volume. So if we assume the liquid does not change its volume, the system is a closed system with constant volume. The steam around this, the steam within the jacket is considered as surrounding, not the system. All right. On the other hand, if the reaction is exothermic, we can change the liquid inside this jacket to be cooling water to receive the extra energy released from the reaction and keep the temperature of the reactant constant. In that case, the liquid inside the system, the cooling water, is also considered as surrounding. All right. Another extreme for closed system is the system with constant pressure. And this picture I show from lecture 1A basically is a glass of whiskey that evaporates. And during that time we said that we can define our system by ourselves. The dotted line here is our imaginary dotted line, or basically we can draw our own system. If we said that the system would go around all the molecule of the whiskey at all time, we can say that the system is basically closed system. But as the whiskey is evaporating, the amount or the volume of the vapor expand. In this case, the volume of the system changes with respect to time. Okay. However, the whole dotted line is under constant atmospheric pressure. So these are pressure, and they are equal to atmospheric pressure. So it doesn't matter how large the dotted line would be, the pressure remains constant. So such system is called closed system with constant pressure. But sometimes looking at this picture would be a little bit more difficult to do the calculation. We can simplify the picture into piston and cylinder assembly. Like in this picture, we can see from this model picture that it is closed system, Okay, if you look from at the picture on the left hand side, you might sometimes think it is open system, but if you look from the picture on the right hand side, it will definitely be closed system, just for your own reminder. Okay, so if this one is the model for the system on the left, we have closed system, but the volume of this system can be expanded, while the pressure outside the system and pressure inside the system remains constant at all time. Inside you may have liquid together with vapor, and during evaporation the piston expands to keep the pressure constant. Such system is called closed system with constant pressure. Okay, so let's analyze each extreme. Okay, let's start with closed system with constant volume. And the first law for such system can be written here. Let me again remind you that first law here, it is universal under assumption that kinetic energy and potential energy change are dropped. Alright. For this particular extreme, the volume of the system is constant. That means no volume change, no expansion work. Alright. I told you from lecture 1b that it is very easy to observe expansion work. Basically, you look at the volume of the system. If the system volume is unchanged, then there is no expansion work. If the such system has no non-expansion work, that means no stirring inside, okay, then W will be 0. Again, under assumption that there is no non-mechanical work. Okay, so let me draw a whole picture again. For the work, that there are two kinds: mechanical work and non-mechanical work. Non-mechanical work will be something like electricity. For mechanical work, it is divided into two parts: expansion work and non-expansion work. Okay, for this particular example, there's no electricity supply to the system, there's no stirring, and there's no expansion. So total work must be 0 in this case. Okay, so W here is 0. In this picture, there will be only heat supply to this closed system. So if you take W in the first law to be 0, the first law will be reduced to delta U total equal to Q. That means, physically, it means the given heat on the right hand side of the equation here would equal to the increase of internal energy. In other words, the amount of energy added to the system as heat would be added on top of the internal energy within the system. Okay? So this equation tells you the change in internal energy of the system. Again, it does not tell you how much internal energy you have within the system. It just tells you that how much internal energy is changed. Okay? The change is equal to amount of energy supplied as heat. And we learned from lecture 1b that there are factors affecting internal energy. There are three main factors: temperature, phase, and chemical bonding. Okay? If the system is assumed to have same chemicals, same phase, let's say it is gas, and it remains as gas, does not change composition, does not have any chemical reaction. So the only factor affecting internal energy right now is temperature. Okay? So in lecture 1b, we said that when internal energy is changed, temperature is changed. And we take temperature to be the indicator to tell the internal energy within the system. Okay? So in this case, when internal energy is changed, temperature would change as well. So when you have increase in temperature, or when you have increase in internal energy, then there will be increase in temperature. Okay, so if I have some meter that can measure the internal energy, of course in real life we cannot measure energy, we can only measure temperature, but assuming that we can somehow measure internal energy, okay, let's say we have a probe that directly measure internal energy. We know that initially the system is at low temperature and has low internal energy. After receiving energy in form of heat, then internal energy is increased and temperature would increase together with internal energy, because temperature is an indicator for internal energy. But the increase itself may or may not be linear. Okay, the function as the red line here can be any kind of function as long as it goes up. All right, so let's say that it goes non-linearly like this in generic form, and then at one particular point, let's say I take this point, I can find slope of this red line by drawing tangent line. The tangent line here, the blue line, tells you the slope at this particular point. We can define the slope mathematically. It is the differential of u with respect to the differential of t. Okay, we define this one to be called heat capacity at constant volume, CV. Okay, so V here as a subscript tells you that the whole change is taking place under constant volume. Okay, under constant volume condition. We also put V here as a subscript, telling you that, just a reminder, that the whole differential here was taken under constant volume. Alright, so if I start at state 1, if 1 is my initial state and state 2 here is my final state after the system receiving heat, for the change from 1 to 2, then we can get the amount of heat from the change in internal energy from first law. From this first law, you just swap these two sides. You can calculate amount of heat supplied to the system. Okay, and then this delta U generically can be calculated from the integration of du from the initial state to the final state. Okay, this is basic calculus. This U is extensive properties, is total energy, total internal energy within the system. There's a T here to indicate that it is extensive properties. If I change from total energy or total internal energy into molar internal energy, we can just split this UT to be N times U, where N is total number of mole within the system. And since the system is closed system, we can take this N out of this integration. Okay? And from this definition, if you take dt from the left hand side to the right hand side, then you get du equal to cv dt, and replace this du to be cv dt here. So basically you can calculate the amount of heat supply to the system so that the state of the system changes from state 1 to 2. Okay, that amount of heat can be calculated based on the integration of cv dt from 1 to 2. Such integration would be integrated for integration of temperature. So 1 here is temperature 1, 2 here would be temperature 2. Okay, in general, this CV, or heat capacity at constant volume, may not be constant. Okay, it can be function of temperature. So you plug this function in there, integrated with respect to temperature, and then you can calculate amount of heat required. For this picture, for this particular picture, when the system is heated, we can imagine that energy after heating would be higher than before heating, and therefore the temperature will be increased as well. But the system walls are rigid, so the volume, the total volume, does not change. Okay, so if the total volume does not change, the molar volume will not change either. Okay, so V2 is equal to V1 at this point. What about the pressure? What about the system pressure? If this gas inside, if this compound inside is in form of gas, what about the pressure? Does it change? If you take ideal gas law inside here, okay, and we learned from high school that P1 V1 over T1 equal to P2 V2 over T2, right? When V2 and V1 are equal, we have P1 over T1 equal to P2 over T2, and T2 is greater than T1. Therefore, according to that relationship, ideal gas law relationship, we will end up with increase in pressure after receiving heat. Okay, so you have to keep in mind that when you try to fix one variable, like when you fix volume in this case, other variable like temperature or pressure cannot be fixed. You have to allow pressure to be increased. Okay, but if we want the system pressure to be constant, what should we do? Okay, in that case, you want to fix pressure. Again, you cannot fix pressure and volume at the same time. If you want to fix pressure and change temperature, you have to allow the system to change its volume. In this case, you have to allow system to expand if you want to put heat in there and try to keep pressure to be constant. All right. And in this case, the volume is no longer constant. That means the whole equation that we have derived have to be re-evaluated. Now the picture looks like this. It will be another extreme of closed system, which is system with constant pressure. So we allow the system to expand, and in order to make sure that we can imagine the system to still be closed system, I'm going to put this piston in there just to make sure that you understand it, that it is still closed system, but the volume can be expanded when the system receives heat. The volume expands to compensate so that the pressure remains constant. Okay, and from this picture you will see that the expansion here is obviously expansion work. Okay, so this is the system expands. That means the system is doing work, and this particular work is expansion work for sure. Assuming that we don't have any stirrer, we don't have non-expansion work in this case, and we don't have electricity, so we don't have non-mechanical work in this case. The only form of work that we consider is expansion work for this particular derivation. Okay. From the first law, the same first law, this first law is applicable for all closed system, all kinds of closed system. Okay. Now in this case, W is no longer zero, unlike this constant volume case. This expansion work from lecture 1b, we derive from the integration of external pressure integrated with respect to total volume of the system. Okay, and I have to remind you that this pressure must be external pressure from the definition. However, from this particular system, we allow we allow the volume to expand so that pressure remains constant. the term constant here means that the pressure here does not change, but also means that this pressure is equal to that pressure at all time. Okay, so P inside the system and P external pressure would remains the same. That means this piston is under mechanical equilibrium at all time. Okay, so in that case, if you integrate this one, the pressure, external pressure is constant, you can take it out of the integration. The rest would be integration of dV. You get delta V out of this integration. And then you can replace this P external to be total pressure inside the system. Okay, because they are the same at all time. By saying that this piston is under mechanical equilibrium at all time, you can also say that the process here should be reversible, right? From the lecture 1b, we said whenever that the system is changing under the condition that they remains at equilibrium at all time, the whole process would be considered as reversible. So in this case, we can say that we can calculate work based on reversible path. Okay. So if we take this W and replace into the first law, we can obtain this equation for amount of heat required. W here, if I take it from here, you can get P delta T, delta V. Okay, note that here that this is total amount of internal energy. This is total volume. Okay, these two variables are extensive properties. And the pressure itself is constant. So I can take it in with inside the delta here. It is constant. I can take it inside. So if it is inside, delta PVT is basically pressure times V1 total. Pressure times V2 total subtracted by pressure times V1 total, right? Then I can take delta out, merging these two terms together to get U plus PV. And also at the same time, replace these external extensive properties into intensive properties, molar internal energy and molar volume. Okay, by changing UT to be NU and VT to be NV, and take the N out of the delta because N is constant within closed system. All right. Now, whatever inside this parenthesis will be defined as enthalpy or H. Okay. Definition here was drawn basically to get something in the same form as this equation. So if you replace these variables within the parentheses according to this definition, you will end up with heat equal to delta H total, which is in similar form at this equation. Okay, basically we draw this definition so that the final equation for these two extreme systems are in the same form, even though the variables are not the same, but the form of the equation will be the same. Okay, such that the given heat for the closed system with constant pressure would equal to the increase in enthalpy. For this system, for system with constant volume, we said that the given heat would equal to increase in internal energy. The amount of energy transferred as heat will be added to internal energy of the system. Okay? For this system, for constant pressure system, the amount of energy transferred as heat will be added to something. that we define as enthalpy. Okay, so sometimes it is confusing because enthalpy is a bunch of variables combined together. It's a defined variables. It's not like internal energy that we can understand. Internal energy has physical meaning, but enthalpy does not have physical meaning. It's basically U plus PV. Okay, but this sentence you need to understand that you give heat and add this heat on top of the existing enthalpy of the system. So enthalpy would be increased by the given heat. Okay, so what is enthalpy? Just to be clear, first, enthalpy is derived properties. It's a properties that is mathematically derived. Okay, and derivation was done basically for convenience. There are two advantages of the definition of enthalpy. There are two purposes. The first one is that we can get this equation for closed system with constant pressure, and we can say that amount of heat supplied to such system would equal to delta H. Okay, in similar manner to the system with constant volume, that amount of heat given to the constant volume system would equal to delta U. We would like to get the same form for system with constant pressure. Another advantage of enthalpy would be shown to you when we talk about open system. Okay. Secondly, enthalpy has unit of energy. It has unit of joule. Okay, but by itself it is not energy. You cannot say that enthalpy is another form of energy. It is not. You have to remind yourself it is just a variable that we define mathematically. Physically, if we try to somehow come up with physical meanings of enthalpy, the closest one would say that enthalpy is the combination of internal energy and expansion work. Okay, it is not really this definition because expansion work should be P delta V, but enthalpy is U plus PV. We look at the term PV in the enthalpy to be the term relating to work, and that work should be expansion work. So sometimes people would say that enthalpy is basically internal energy accompanied by expansion work. Okay, that means if you look at the definition, H equal to U plus PV, any factor affecting U would affecting enthalpy for sure. Okay, so temperature, phase, and chemical bonding would definitely affect enthalpy, just in the same manner as they are affecting internal energy. So if we have similar forms of equations, this one for constant volume, this one for constant pressure. Again, if I have a probe that can directly measure enthalpy, and you see that initially for this system, enthalpy is low simply because internal energy is low. Okay, and temperature would be, which is the indicator of internal energy, and it is indirect indicator of enthalpy, would be low as well. Okay, when you supply heat or supply energy as heat into the system, then internal energy would increase and enthalpy would be increased as well. So the final state should have higher enthalpy than initial state and higher temperature as well. So the function would be something like this. Okay, it can be linear, it can be non-linear at any form, and it might not be the same as this graph. Okay, but it would be the increasing function. You can find slope at any given temperature, and that slope will be defined as heat capacity for the constant pressure process, or CP. This slope mathematically can be written as dH by dt with respect to, dH by dt for the whole process under constant pressure. Okay? Please keep in mind that this differentiation is partial differentiation. Same here. Both of them are partial differentiation, simply because enthalpy or internal energy are a function of so many variables, and temperature is just one of them. Right now we differentiate it only with respect to temperature, so therefore we put it as partial differentiation. Alright? So starting point is state 1, ending point is state 2, okay, in general. So the delta H can be calculated from integration of dH from 1 to 2, changing extensive properties to intensive properties. This is molar enthalpy. You take the number of moles out, okay, and this can be drawn outside the integration because n is constant for closed system. And replace this definition, dH would equal to Cp dt here. So you see that at the end, the equation remains very similar, in similar form. This is Cv, this is Cp, but they are in similar form. What about what we learned from high school? In high school, we used this simple equation. Heat would equal to mc delta T. Okay? But right now in thermodynamics, we have two equations. Q equal to n integral of Cv dt and integral of Cp dt. Are they different? Are they the same? How can we relate them together? Okay. First of all, why in high school there's no integration? Okay. If you look at these two equations, you see that if the heat capacity, either Cv or Cp, is constant, if it is constant or if it is not a function of temperature, then you can take it out of the integration, and the remaining integration is basically dt, integral of dt, you get delta T, right? And then you end up with this same equation here. So in your high school, basically you use heat capacity under assumption that heat capacity is not a function of temperature. That assumption is valid only for the small range of temperature. Okay? But in engineering application, temperature range is much wider. So we have to be very careful and also consider that within that wide range of temperature, heat capacity is now a function of temperature, and we have to use integration form. Okay? The second question is, should we use m, mass here, or n, which is number of mole? Which one is it? They are related basically. If you use mass, this heat capacity would be called specific heat capacity. The unit of heat capacity should be joule per kilogram per Kelvin. Okay? On the other hand, when you use number of mole, this heat capacity will be turned into molar heat capacity with the unit of joule per mole Kelvin. Okay? So you can still use this form, changing this n into mass, and then you have to change this molar heat capacity into specific heat capacity. Okay? The last question would be, is that Cv or Cp? In your high school, it's basically just plain C, or we call it heat capacity only, plainly. But in the thermodynamics, we have to define whether it is heat capacity at constant volume or heat capacity at constant pressure. Okay? So this one in particular from high school, is it Cv or Cp? Again, you have to understand, in your high school, this equation was applied mainly for liquid or for solid. Okay? And liquid and solid does not expand that much when you heat it up. So when there is no big expansion, okay, heat capacity at constant volume CV and CP are about the same. They are the same value or roughly the same value because expansion is negligible. Okay, delta U and delta H are roughly the same. If you take delta H from its definition, delta H is delta U plus delta PV, right? And delta PV corresponds to change in volume from the expansion when you heat it up. And solid and liquid does not change its volume that much when you heat it up. So that term would be dropped and you get delta H and delta U to be the same. Therefore, this heat would be the same either way. Okay? So, for this part of the lecture, I just put some details in the calculation of first law and divide them into two extremes: closed system with constant volume and closed system with constant pressure. In reality, the change that we have might not be either one. It might be somewhere in between. That means you may have change that changes are done both in volume and pressure. Okay, you might have change that both volume pressure are changes at the same time. That would be in the middle. Okay, that would be calculation in the middle of these two extremes. But just for simplicity, we have to consider two extremes first. Okay, there are two variables that were introduced in this lecture. The first one is heat capacity, and you have to be very careful whether heat capacity will be at constant volume or at constant pressure. The other variable that we consider is enthalpy, and enthalpy was defined based on system with constant volume. But it doesn't mean that you cannot calculate enthalpy in the system with constant volume. Oh, I'm sorry. Enthalpy was defined based on system with constant pressure. Okay, but still you can be able to calculate enthalpy for system with constant volume. But it might not be very useful when you calculate with constant volume system. Alright, so this is the end of this part. Thank you for watching.